Hello and welcome back to myself CAC, and this lecture is a continuation of the previous lecture on the computation of the multilayer perceptron. So we were talking about the activation function, and this activation function adds some non-linearity to your model. So it determines the extent of the neuron's activity, like every neuron has a particular activation state, and whether this neuron will be activated depends upon the input the neuron receives, the present activation state of the neuron, and a threshold value that is fixed for that neuron. As you can see in this particular equation, this is for some neuron J for a particular time step t, where it receives an input net jt. It is already in an activation state AJ minus 1. So t minus 1 signifies the activation state at the previous time step, and theta j is the threshold that is fixed for this neuron j. So this activation function is globally defined for the entire neural network, or at least a set of neurons, but this threshold value is unique for each neuron, and this is changeable. This is the generic activation function that we apply, but we actually have some activation functions that we heavily use in deep neural network. So let's go through some of those popular activation functions. So the easiest among them is a Heaviside function, where whenever the input crosses a particular threshold value, the value of the output value of the neuron changes from one value to the other, and otherwise it remains constant. So this is a graphical illustration of the Heaviside function, where y-axis determines the value of the function and x-axis determines the value of x. So as you can see that the threshold point here has been fixed to 0, or we can say that whenever the input x is something positive or 0, the neuron gets activated. That is, the value of this function changes to 1 from minus 1. So minus 1 you can consider an off state, and plus 1 you can consider an on state of the neuron. But the problem is the Heaviside function is not differentiable. Now, why do we need this property? See, when we assign the weights to those hidden layers and those output layers, we do that randomly. So we actually, when as the training takes place in a neural network, those weights are adjusted to fit to the model, to fit to the true value of the output that the model intends to find out. So we need to differentiate the error, and we need to differentiate the previous values that we get in order to do that. And I'll make a different video on backpropagation. So for now, you have to just remember that these functions need to be differentiable in order to make this backpropagation work. Now there are different ways to adjust those weights, but backpropagation is very widely used. So Heaviside function, as we can see at this threshold point, that is when x is equals to 0, this is not differentiable because it jumps from minus 1 to plus 1, and since these minus 1 and plus 1 are constants, so for other values of x, the value of the differentiation is 0. Now moving on to the next function, we use a rectified linear unit function, or the ReLU function, where this is the equation of the ReLU function, where it outputs the value of the maximum of x and 0. So what it does, it transmits only the positive values. As you can see in here, this is the value of x. So for any value less than 0, the value the value of the neuron, the output value of the neuron was 0, and as the value changed from 0 to positive, as x started taking positive values, the value of this ReLU x changed accordingly. Now if we take the gradient plot for this ReLU, we can see that well at this when the value of the value of x is negative, the value of the differentiation is 0. When the value is positive, this is taking the value of 1. Now at this point there is a problem. At the point 0, again this is jumping from this value 0 to value 1. So what we take is, when the value of x is 0, we take the left hand side derivative, and we have fixed that the derivative at point 0 in ReLU function is 0. And then we have another variation of this ReLU function, which is known as the parameterized rectified linear unit. So previously, as we can see, that it was not transmitting any value other than the positive values, but this p-ReLU has another factor, that is plus alpha minimum of 0 and x. So when we feed positive values into it, minimum of 0 and say 2 or 3 or whatever, it will be 0. So only this p-ReLU function changes into a ReLU function where the value of x is positive. But when the value of x is negative, so depending upon the value of this element alpha, so this alpha is a positive number, you can call it a hyperparameter. So this depending upon the value of alpha, some say alpha x will be transmitted into as output from this neuron. Now, next we move on to a very important function known as the Fermi function or the sigmoid function, which is equals to 1 by 1 plus e to the power minus x. So what the Fermi function does is that whatever be your value of x, it plots that from a value of range 0 to 1. As you can see, this the curve of this sigmoid function when plotted looks like an S, and at this point, say at point 4 point, or should I say 3 or 4, the value of the sigmoid x is 1, and thereafter from this point the value remains a constant. Similarly, the value at the point minus 8 or minus 6 is a 0, and at this point the value starts changing. So this is a very much differentiable kind of a function, and if you take a ddx of sigmoid x, it is equivalent to e to the power minus x by 1 plus e to the power minus x whole square. This is the plain differentiation that you have learnt in your school, and if you manipulate that, this is equivalent to sigmoid x into 1 minus sigmoid x if you take this value. Now if we plot the gradient of this sigmoid function, we can see that at the point 0, the value of the gradient of the sigmoid function reaches the maximum value of 0.25, and as the value moves towards higher values in both negative and the positive quadrant, the value approaches 0, because it approaches the constancy. At this point at minus 8 or at 8, the value is a constant in this sigmoid curve. So naturally the gradient of this function at high values in both negative and positive quadrant will move towards 0. Now we have another form of a sigmoid function, which is a sigmoid function with a temperature parameter. So previously it was 1 by 1 plus e to the power minus x. Now we have this has been changed to e to the power minus x divided by t. Now this t is known as a temperature. So if we plot the value uh, against a graph, so what we see is as we decrease the temperature, see at this point the temperature is T. At this point the temperature is T by 2. So the curve is sharper. It's getting, see, sharper. This is at T by 2. This is at T by 5. This is at T by 10. And finally at T by 25 the function looks like this. So this is almost like your Heaviside function. So it helps with manipulation, like how sharp you want your curve to be. That depends upon what your model is trying to find out. So lower the temperature, more the function is compressed towards the x-axis. Next, we move on to the last function, the hyperbolic tan function, which is equivalent to e to the power x minus e to the power minus x divided by e to the power x plus e to the power minus x. So what it does is it puts the value of x within a range of minus 1 to 1. So when we differentiate that, when we take a ddx of tan hx, it is equivalent to 1 minus tan h square x. So when we plot the gradient of the tan h plot, tan h function, so what we see, it's just like the sigmoid. At the point 0, the maxima is reached in this gradient and that value is 1, and as we approach towards higher values in any of the quadrants, the positive or the negative quadrant, the value approaches 0. That is, it takes a constant value when when the values are 0, when the values are further away from this 0, that is at point minus 6, this is minus 1, and at point 6 this is plus 1. So it takes a constant value, and for that reason the derivative approaches 0 for these points too. So that is all about the activation functions. If you have liked the video, please give me a thumbs up, and thank you for watching.